An introduction to nuts and bolts. What I want you to get out of the module, so this preparation and the assignment as well, I want you to be able to identify the essential dimensions of a thread and read a thread designation. Like quarter 20, what does that mean? So first, some terminology. How do we refer to the different parts of a thread? Well, the top of it, the peaks of the threads, we call the crest. And associated with the crest is a major diameter of the thread. Whether that's a threaded fastener or a power screw, it has a major diameter. That's the outer diameter. We refer to it with the symbol plain old D. Another way to think of D is what is the smallest hole that this thread can possibly fit in. It will have that diameter D. The valleys of the threads we call the root, and associated with the roots of the threads is the root diameter, also known as the minor diameter, but we give it the symbol D sub R. R is for root. Now I've talked about these as though they were distinct threads, but actually this is one continuous thread that's rolled around in a helical shape around, you can think of the minor diameter in a sense. It's as though you took like a triangle or a triangular prism and wrapped it around. So it's actually one single thread. If I start here and I go around 360, I'm going to find myself over here. But we can talk when we view it from the side as though these were adjacent threads and separate. And so the pitch is the distance between these separate threads, or when viewed from the side, one thread to the next. That's called the pitch. And we give it the symbol P. So D for major diameter, D sub R, or root, for minor diameter or root diameter, and P is our symbol for pitch. And the last symbol on this slide that we're going to learn is alpha. That is the thread angle. You can think of it in two different ways. If you look at the angle between one thread from the side and the vertical here, well, that's our alpha. Or the thread angle is 1/2 of the angle between adjacent threads. Another way that you can think about it is, well, that's the same angle as this triangle here. You imagine that the thread form is a triangle. Well, the thread angle is 1/2 of this angle of the triangle. Okay, some more terminology. We also have a mean diameter. This is given the symbol D sub M. M is for mean, not for major. So back in the previous slide, the major diameter of the thread, the outer diameter, just had the symbol D. D sub M is for mean. And that is just the mean, the average of the outer diameter D and the root diameter D sub R. Now we also have a conceptually distinct diameter that we call the pitch diameter, and we give that D subscript P, P for pitch. Now these turn out to be equal in many cases for many thread shapes, but they're conceptually distinct. The mean diameter is simply the average of the major and minor diameters, but the pitch diameter is the diameter at which the thread thickness, so the distance from one side of the thread to the other, you can see how that thickness changes. At the root here, it's a lot thicker than here at the crest, while there is a certain diameter at which the thickness of the thread is 1/2 of the pitch, and that is called the pitch diameter. So distinct ideas, but often numerically equal. Now the pitch is the distance between adjacent threads. So think about if I were an ant and I'm walking around the crest of the screw here, and I follow it, and I come back, I go a full 360 degrees, and I end up here. I traveled a certain distance along the axis of the screw. That's the same distance as if I turned this screw 360 degrees. If I rotate it into a nut or something, how far does it translate? Well, it's the same distance that the ant that's traveling around the crest would travel in the direction of the axis of the screw. Those two ideas are equal. Now, pitch is when we look from the side and we see what this distance is. That's conceptually distinct from L, the lead. It's the distance that the screw travels axially in one turn. So how is this related to the pitch P? Well, yeah, you guessed it. For a single start fastener or screw thread, then the pitch is equal to the lead. However, there are also multiple start threads. Like if you've been in the machine shop, You'll see end mills, and they might have 3 or 4 starts to them, multiple flutes on the end mill. And it's several helixes wound together. And so let's take a look at how this idea of L, the screw lead, the distance that the screw travels when you turn it around once, and the pitch are related when there are multiple starts. So this here, like, let's imagine that this is the crest of a screw and everything else is gone about the screw. We're just looking at that, and it would look kind of like a sine wave if we view it from the side here. And the distance that if we were an ant that we would travel, if we started here at the bottom and we went around 360 degrees, we would travel axially along the axis of the screw a distance L, the lead. If there are multiple starts, let's have a second start here, we have a totally separate thread. If you're on the red thread, you never end up on the blue thread. Right? We can see by the way that they cross here, right here, the red thread is on top and the blue thread is on the far side of the screw. And over here, the blue thread is closest to us and the red thread is on the other side of the screw. And they never touch. We're still going to call from the side the distance between adjacent threads the pitch. So you can see that these are conceptually distinct. L is the distance that you'd travel if you go around 360 degrees. P, the pitch, is the distance between adjacent screw threads. So when you have multiple starts, there is a relationship between them. You can tell that the pitch is half of the lead. The lead is 2 times the pitch because we have 2 starts. If you have more starts than that, well, here's the general idea. The lead is the number of starts times the pitch. Okay, back to thread angle. Remember that this can be viewed as the half the angle between adjacent threads, or you can think of it as if the screw thread is like a triangle that's going to be wrapped around a cylinder, then twice the thread angle is the angle of that triangle. The thread angle is 1/2 the angle of that triangle. That's conceptually distinct from another important angle that we have when we're talking about screws. This here's the thread angle, but take a look at something different here. If we zoom in here, and look at it really closely, well, you can imagine there is a vertical line that we could draw, and then we could say, what is the tangent line to where the crest is traveling? You can tell that there's a difference between pure vertical and the angle that the crest is going at. We call that angle lambda. This is the lead angle. We can also look at it as the angle that this triangular shaped thread is wound around the cylinder. So these two things are conceptually distinct, and they don't have actually, they don't even have a numerical association with one another. The thread angle is not really something that we can calculate from the other things that we have. There are all sorts of different thread angles. Common fasteners, the thread angle is about 30 degrees. Certain power screws are 0 degrees or 14.5 degrees. So the thread angle is just determined as a matter of convention. The lead angle is something that we can calculate from the other things that we have. So this is how the lead angle is actually defined. We don't actually look at the crest of the screws. Imagine you're an ant and you're walking on the surface at the mean diameter. And you walk around 360 degrees. Now, how far did you travel? Let's imagine you took your path and you wanted to figure out how far you traveled. We've unraveled this path that we've traveled into a straight line here. Now, imagine a second ant that's going around a cylinder with the diameter equal to that mean diameter, d sub m, and we just go around 360 degrees and we don't follow the helix. We just go around the diameter of our cylinder and we come back to where we started. Well, how far have we traveled? Well, we've traveled in a circle that had a diameter of d subscript m, the mean diameter. So we've traveled pi times the mean diameter. And this is the relationship between those two things. If I am the ant that's traveling strictly around that cylinder, and I've gone pi dm, versus if I am traveling around the thread, I've gone a different distance. And there's a certain angle between these two paths. Now the third leg of this right triangle here is the lead. This is how far We moved axially if we were the ant that was traveling around the helical shape. So if we travel along this unraveled helix, we also go up a distance in the direction of the axis by an amount equal to L, the lead. And this angle here is lambda. That's the lead angle. So if we know the lead and we know the mean diameter, then we can figure out what lambda is. Tan of lambda is L over pi dm, sine over cosine. And so we can solve for lambda there. The lead angle lambda and the thread angle alpha are not related. So let's do an example. What's the lead angle of a quarter 20 bolt? We haven't learned to read thread designations yet, but you might know that quarter refers to the major diameter of the bolt, D, and 20 refers to the number of teeth per inch of the bolt. So I'll give you some additional information. First of all, there is a table in the book that has some information about these different thread forms. For different sizes of screws, it'll give you the major diameter. Well, that's usually apparent from what the name of it is. Tells you the number of threads per inch. Well, that's also apparent from the number as well. And it gives you some other things, but it's not going to give you this lead angle. So we're going to have to figure that out. They do tell you that the minor diameter for a screw is found from the equation d sub r is d minus this constant times p, the pitch. And I'll tell you that using this information, we can calculate the lead angle. So how do we do that? Well, the tangent of the lead angle, let's write that equation down, is the lead, L, divided by pi times dm, the mean diameter. Now, what is the lead? This is a quarter 20 bolt, so there are 20 of these teeth per inch. So what is the spacing between adjacent threads? The pitch. Well, the pitch is just 1 inch divided by, get shared equally between the 20 of them, the 20 of the threads. And so that's 0.05 inches is our pitch. Now, we have a single start fastener, so this is also the lead. So that's our L. L is equal to 0.05 inches. dm is the mean diameter. Now remember, that's not minor, that's not major. dm is the major diameter plus the minor diameter, or the root diameter, divided by 2. Well, we've got d, and then let's actually calculate dr separately. We could, dr is d minus 1.299 times p. Substituting, d is 0.05. We get that the root diameter is 0.185 inches. So the mean diameter is the average of this and d, the 0.25. That's 0.2175 inches. All right, so now we can find what lambda is. The lead angle is the inverse tangent of 0.05, or L, over pi times the mean diameter, 0.2175. This is 0.05. And that's 4.185 degrees. You can see that's pretty different from the thread angle alpha, which is for a quarter 20 screw is going to be 30 degrees. So very different numerically and conceptually. So next time we're going to learn to calculate the proof load of the bolt. We won't talk about what that is yet, but the next important parameter of a bolt is the tensile stress area. And that is an area of a circle that has a diameter that's equal to the mean of the pitch diameter, which we talked about before, and the minor diameter. So again, here's our screw thread, and we have the pitch diameter, which is that theoretical diameter at which the thickness of the thread is 1/2 of the pitch, and the minor diameter is the diameter of the roots of the threads. So the tensile stress area, it says the area of a circle with diameter equal to the mean of these two. So it's not the same as the mean diameter. The mean diameter, d sub m, was the mean between the minor diameter and the major diameter. Now we're going to take the average of the minor diameter and the pitch diameter. We're going to square that and multiply it by pi over 4, and that gives us our tensile stress area. So this is effectively the area over which stresses are carried in the bolt. So if you want to figure out what the normal stress in a bolt is when it's being pulled apart, well, it's approximately equal to the load over the tensile stress area. This is going to help us figure out what the strength of a bolt is and how much load it can handle. If we know the strength of the material it's made of and we know the tensile stress area, we can figure out how much load that the bolt can handle. Now these things are tabulated in 8-1 and 8-2 in the book, but let's figure this out too. Let's do an example. What's the tensile stress area of a 1/4-20 fastener? So as you can see, we can check ourselves. If we look inside this table in the book, the tensile stress area is tabulated, both for coarse series bolts and for fine series. We'll talk about the differences between those. Remember that minor diameter, which we're going to need to calculate the average of the minor diameter of the pitch diameter. It's found from this equation, and the pitch diameter is found from this equation. So we're going to calculate the mean of those two. And the mean of the pitch diameter and the minor diameter is used to compute the tensile stress area. So let's go ahead and do that. We've already found what the minor diameter is. Let's figure out what the pitch diameter is. D subscript P is D, 0.25 inches, minus 0.649519 times the pitch P, which is 0.05. Substitute those in. We get 0. Now this might look familiar. That's what we got for the mean diameter above. So as I mentioned before, even though the pitch diameter is conceptually distinct from the mean diameter, they're numerically equal for regular threads. All right, our minor diameter from before, DR is 0.185. And in order to compute the tensile stress area, we need to take the average of those two. So the tensile stress area is pi times the average of those divided by 4. Oh, we got to square this. Run the numbers, and I get 0.03182 inches squared. And let's look that up in table 8-2. We look for the size designation. We have a 1/4-20. So 1/4-20 bolt 0.318 is the tensile stress area, 0.318 here. And that's what we got. So here's a quiz. What is this called? Think for a second. That is the thread angle. How about this one? That's looking at the diameter of the crests of the threads. That's called the major diameter, and it's given a symbol D subscript M. How about this one? Well, you can think of it for a single start fastener. It's both the lead and the pitch, but really what we're depicting here is the pitch because it's the distance when seen from the side between two adjacent threads. If there were multiple starts, it might be different from the lead. And this one here, that's where the roots are, and that's the diameter associated with the roots of the threads. That is the root diameter or the minor diameter, D subscript R. Some more information about thread designations, so you know the basics, 1/4-20. Well, we've got two systems. We've got the unified or American national system, and we've got the metric system. For both of them, the thread angle is 30 degrees. A basic thread designation from the unified system is 1/4-20, and we write a UN after it, just to be even more explicit that we're talking about the unified threads. First number there is the diameter, typically in inches, and then the second number is the number of threads per inch, the inverse of the pitch. Now for the metric series of threads, we have an M that's indicating that it's metric, and then it indicates the diameter in millimeters. And this M is important here because sometimes this number here is not a diameter, sometimes it's a gauge number. That M is very important because if this didn't have an M here, you might think that it was a unified thread that was gauge 10, but the M tells us it is a metric thread. The second thing that tells us a metric thread is you kind of get to know the number of threads per inch that are associated with common unified screw sizes? Well, this here is the pitch for the metric thread. So this is 1.5 millimeters pitch. So there's usually a major difference between the two numbers because this one is threads per inch, which is the inverse of the pitch. How about if you see a designation that looks like this? Well, here's an example of the diameter or gauge number that we might see on a unified thread. And when you say UNR, the R means rounded root. That's at the base of the thread. Instead of making a sharp angle to head over towards the next thread, they put a fillet in there. And that helps with stress concentrations. We've talked about a little bit stress concentrations when you've got changes in the geometry. You try to like smooth those out. And so those rounded roots do a little bit better under fatigue loading when there could be cracks that propagate because of these stress concentrations. For metric threads, rounded roots, you can get those as well, but they designate that with a J. And so here's a MJ10 by 1.5 is a metric rounded root thread that's 10 millimeter major diameter and 1.5 millimeter pitch. F is something else you can have. Now notice this was a 10-24, so 24 threads per inch for a 10 gauge for the regular UNR thread, but a 10 gauge thread can also have 32 threads per inch if it is of F, the fine series of threads. Metric has fine threads as well, and you'll see them like MJF. So the 10 millimeter major diameter fine thread has 1.25 millimeter pitch. And these J's and F's are not always together, nor are the R's and F's always together up here. You can have just an F, you can have just an R, etc. So think about fine threads. The threads are smaller. What's some good things about it? Well, if the thread is smaller, but the major diameter is the same, what do you think? Is the thread going to be stronger or weaker? Well, if the major diameter is the same, but it has smaller threads, so it has a larger root diameter, then the tensile stress area is going to be bigger and it's going to be stronger in tension and it's in shear. Also, if you're screwing it, right, you're turning it, sometimes you want to be very precise about how much force you're clamping two things together with, or maybe you're using the screw as like a set screw, and so you're using the screw, turning it to set some distance between two parts. You get finer adjustments with a fine thread. The lead is smaller. Also, you need less torque, you might imagine, to develop the preload or clamping force. If you're trying to clamp two things together, it requires less torque in order to develop the same amount of force because that lead angle is smaller. And for associated reasons, it turns out that that makes it less likely to loosen on its own. And these smaller threads, because you don't have to dig as deep, if you're using taps or if you're using dies to cut the male threads, it's going to be easier to tap because you don't have to cut as much material away. Now, there are some cons associated with them too. They're more prone to galling, damage, and seizure. They're just more fragile. Galling is when you have two materials, try to drag them with respect to each other, and they kind of stick together. But microscopic amounts of material from one part ends up on the other part. It's going to ruin your threads. So other kinds of damage can result for fine threads. And this is a big con. So the general tip is to use coarse threads, regular threads by default. If you need these things and are willing to accept the risk that your threads might get damaged, then especially if they're permanent, that's probably okay. You can probably set it and forget it. Then you can consider the fine threads. Now, just a little bit about power screws. We talked about threaded fasteners have a thread angle of 30 degrees. Well, power screws, which are used for power transmission, like think of the screws that are on a lathe or on a C-clamp or on certain kinds of car jacks, you might see that they could have a square thread. Now here's some of the dimensions shown. D, here's the major diameter of the square thread. You might imagine this is the axis and you've got threads on the other side as well. We're just seeing half of the profile here. The root diameter, and it turns out that the height of these teeth is P/2, where P is the pitch. So square threads have some nice geometric simple properties. There's also Acme threads. Instead of having alpha equals zero thread angle, right? The angle between two adjacent threads is 0 degrees. Half of that is also 0 degrees. Alpha is 0 degrees. Acme threads have 29 degrees between threads, so the alpha is 1/2 of that is 14.5 degrees. But they still have the nice property that the height of the teeth is p over 2, and the difference between the major and minor diameters then would be p. Same for both square and Acme. The difference between the major diameter and the root diameter is just p. So square threads have an alpha of 0 degrees, and alpha for the Acme threads is 14.5 degrees. Now, what are the advantages of these two? Let's first think about friction and which one is going to require more torque to turn under a given load, right? These things are for power transmission after all. So which one is going to tend to have more friction? Well, let's think about something just a little bit simpler. Let's think if we have a cylindrical sort of shape here. This is rotated around an axis, and it's sitting, this is just a cross section of a cylindrical tube that it's sitting on. And you've got a cut between the surfaces, and there's a pretty shallow angle. It's almost like you just cut the tube flat and you almost cut this cylindrical part. You almost cut that off flat, but no, you cut them with a slight bit of an angle. And you pull down on this red part with some force F, and you try to turn it. How much torque is it going to take to turn it? If you're applying a certain force F down on it, there's going to be friction between these surfaces. If you try to rotate this red part, it's going to require some torque to turn it. Now, what if we made that wedge angle, this angle here, a lot steeper? You apply the same force downwards. How much torque is it going to take to turn that? Which one is going to require more torque under a given load? F. Well, let's think about it a little bit. This is akin to the thread angle of a screw, it turns out. This is very similar. So we're going to call it alpha, this angle that we cut this thing at. And the surface normal to that is the direction that you're going to have that normal force. And I think that you'll agree that the friction force is proportional to that, and so is the friction torque. So the torque that's going to be required to turn this thing, T1, is proportional to whatever that normal force is. So we're going to be interested in which has a greater normal force, the relatively flat one or the wedge-shaped one, the small alpha one or the large alpha one. Well, this force needs to get supported by, well, as viewed from the side, 2 times n, this normal force, times the cosine of alpha, cosine of alpha. So the smaller alpha is, the more aligned with this force that these normal forces are, and the smaller that they need to be in order to add up to the total force F. Another way you can look at it is we rearrange the equation. We find that the normal force is F over 2 times the cosine of alpha. And if you remember before, we said that the torque is proportional to the normal force, so we can make the argument that the torque is proportional to 1 over the cosine of alpha. So if alpha is small, say 0, then the cosine of alpha is 1, and so this ratio is 1. If you make alpha a larger number, say 14.5 degrees for the Acme thread, then the cosine is going to be smaller. 1 over that number is going to be larger. The torque is going to be larger. So the larger alpha is, the greater the torque is going to need to be. So one of the pros of a square thread is that it's going to be more efficient. Because alpha was 0, the torque required to turn it is going to be smaller. However, some cons are that it's not quite as strong as an Acme thread. If you look at the angle of those threads, these square threads are not as strong as these ones, right? Because if you're applying some load, because it's the female thread and you're pushing down, that puts these threads kind of in shear. Square threads have a smaller thickness here at the base than the Acme threads do. So the Acme threads tend to be stronger because that's where the stresses are going to be highest, is kind of at the base of these little beams that are sticking out. So Acme threads are stronger. They're not quite as efficient because they've got a greater thread angle, but they are stronger. And another disadvantage to the square threads is that they tend to be more difficult and expensive. slower to machine. And that's because there's less room for chips to get out. You can imagine with these Acme threads, you can fit a tool in there, and then there's a little bit more room for chips to get out of the way. Whereas with these square threads, you're digging in there and there's nowhere for the chips to get out. So that was threads. I hope you can now identify some of those essential dimensions: the major and minor diameter, the pitch diameter, the thread angle, the lead angle, and also read thread designations, quarter 20 UNC MJ10 1.5. And actually, we learned quite a bit more than that. But you're going to have to be very familiar with these important dimensions and the symbols that go along with them and thread designations in order to move on with our study of threads.